Imagine writing like a flawless, meticulously tested recipe for a cake.
Okay, I'm with you.
You use perfect measurements, precise temperatures, crystal clear instructions, and you hand it over to a world-class kitchen.
Right, should be a masterpiece.
Exactly.
Mm.
But when the cake comes out, it tastes like a leather shoe.
Oh, wow. What went wrong?
Well, somewhere in that kitchen, a prep cook decided to read your English recipe using a French dictionary.
Ah! Yeah, that'll do it.
The ink on the page didn't change at all, but the environment completely scrambled the meaning. And that silent, invisible failure is happening every single day in the hidden architecture of the internet.
It really is. I mean, it's a programmer's ultimate nightmare. You build something logically perfect only to watch it get mangled by the very systems that are meant to assemble it.
Right.
You can't just be an architect anymore. You basically have to be a defense strategist.
And that is exactly the journey we are going on today. Welcome to the Deep Dive.
Glad to be here.
Today we are unpacking a really fascinating diary entry from a programmer named Ang. This was published on July 3, 2026.
Yeah, the title is Notes-on-Haskell-Programming, Part 177, Concise ASCII Characters Mapping to Full-Width Equivalence.
Which I know sounds like an incredibly dense wall of tech jargon.
Yeah.
But I promise you, we're going to look at how a developer cleans up their digital workspace, discovers this beautiful mathematical harmony hidden inside their code, and then immediately has to build a titanium wall around it.
Just to protect it from the outside world, it's a great narrative.
It really is. So what stands out to you in this specific entry? Because we're catching the author right after a victory, right?
Yeah, exactly. The mindset here is what's so interesting. Ang had just successfully written this program to parse Chinese numerals in chapter headings and convert them into standard digits.
The feature actually works.
Right. It works perfectly. And, most developers at that point would just check the box, push the code, and move on to whatever the next ticket is. But Ang stops.
Ang looks backward.
Yeah. Ang stops and says, wait, let's look at how we did this.
Because the code works, but it's messy. The diary notes that the original solution was written to prioritize, quote, readability.
Right. Which is usually a good thing.
Usually. But it featured this massive hard-coded mapping table. We are talking about 90 lines of code that literally just listed out every single standard character and matched it to its wider full-width counterpart.
Just brute force.
Yeah, so line 1 is standard A maps to full-width, line 2, B maps to on and on 90 times.
And Ang decides to just delete all 90 lines.
Right. And here is where I get tripped up, honestly. Ang claims that deleting this massive list makes the code more readable. But wait, let's unpack that. To a human being, isn't a direct A to B dictionary the most readable thing possible? If I want to know what happens to the letter X, I just look at the list. How is hiding that mapping an improvement?
Well, you have to think about the cognitive load of navigating a system like that. On a micro level, looking at a single line, sure, yes, it's explicitly readable.
Right, you see exactly what X becomes.
Exactly. But code isn't read in isolation. Code is a living system. So when you open a file and the first thing you see is a 90-line block of repetitive boilerplate, it completely dominates your visual space.
It's just a wall of text.
It is deafeningly loud. You have to scroll past this giant wall of data just to find the actual logic of the program.
It's like opening a novel, but the first 3 chapters are just a glossary of every word the author's going to use in the book.
That's a great way to put it.
You haven't even gotten to the story yet, and you're already exhausted.
Right, that captures the friction perfectly. In system design, there's this fundamental difference between explicitly stating data and expressing a rule.
Unpack that a bit.
Well, a 90-line mapping table is just brute force data entry. It tells you what is happening, but it completely hides the why. And if you're a human reviewing that code, your brain has to manually verify every single line.
Oh, to make sure there isn't a typo.
Exactly. What if line 47 accidentally maps an M to an N?
You would never spot it. Not in that sea of text.
Never. So true elegance in engineering is about stripping away that noisy data to reveal the underlying mechanism. By deleting those 90 lines, Ang isn't hiding the truth.
Ang is clearing the brush.
Yes, clearing the brush so you can see the actual foundation of the forest.
Okay, that makes sense. You want to see the rule, not just the raw output of the rule. But, if you delete the map, the computer is suddenly blind, right? It doesn't know what X becomes anymore.
Right, you can't just delete it and walk away.
So how do you give the computer its sight back without pasting those 90 lines back in?
So this is where the magic happens. The solution lies in Haskell's list comprehensions, combined with a really deep understanding of how our text is actually encoded behind the scenes.
Okay.
Ang replaces that entire 90-line table with a single, highly concise loop. The code basically tells the program to look at the standard ASCII range. Specifically, it starts from the space character right through to the tilde character.
Just to ground that for a second for everyone listening, that space to tilde range basically covers the entire standard English keyboard, right?
Pretty much.
It's your uppercase, your lowercase, numbers, and all your basic punctuation.
It is the core foundational block of digital text. But to understand the brilliance of what Ang does next, we have to talk about what a full-width character actually is.
Right, because that's what we're mapping to.
Exactly. Historically, in Chinese, Japanese, and Korean typography, especially on early computer terminals, characters were designed to fit perfectly into a fixed square grid.
Okay, so they all take up the exact same amount of space on the screen.
Yes. But standard Western ASCII characters, like a lowercase I or an L, are very narrow.
Right, so if you put a skinny English I next to a really dense, complex Chinese character, it looks visually unbalanced.
The spacing is completely off.
Right.
So to fix that visual imbalance in mixed language text, systems introduced full-width versions of the standard ASCII characters.
Right.
They are exactly the same letters and numbers, but they are drawn wider. They're padded with empty space, so they take up the exact same square block as a Chinese or Japanese character.
So full-width characters are essentially standard letters wearing shoulder pads so they fit in with the crowd.
That is a hilarious but totally accurate way to visualize it. But here's the catch. They are completely distinct characters as far as a computer is concerned.
Oh, really?
Yeah, an ASCII A and a full-width brute have completely different identities in the machine's memory. In a brute force world, you would have to map them one by one.
Which is the 90 lines of code.
Exactly. But the architects of the Unicode standard didn't just, throw these full-width characters into a random pile. They built a meticulously planned mathematical grid.
Oh, so there's a pattern.
A very rigid pattern. Ang realized that the entire block of ASCII characters maps directly to their full-width counterparts through a fixed hexadecimal offset.
And that magic number, the offset that shifts everything over, is 0x feet.
That is the key to the entire refactor, 0x feet. In decimal numbers, that is 65,248.
So the distance between every single standard character and its full-width partner is exactly 65,248 spaces in the Unicode table.
Every single one.
So it's literally just basic addition. You don't need a dictionary. You just need to know the starting coordinate and add the offset.
Yep. And the mechanism in Haskell to do this is just beautiful in its simplicity. Ang uses two built-in functions, from enum and toenum.
Okay, how do those work?
First, from enum strips away the visual glyph, the actual shape of the letter on your screen, and it pulls the raw underlying integer value of that character.
So it looks at the letter A and says, your numerical ID is 65.
Exactly. And then you just add the 0x feet offset to that 65.
And then what?
You add the offset, and then you wrap it in the toenum function, which casts that new, much larger number back into a character glyph.
Oh, wow.
And the output is flawlessly, perfectly the full-width version of A.
It's like playing a piano. If you have a melody in your head and you want to transpose it, the brute force way is to rewrite every single note on a new piece of sheet music.
Right, which takes forever.
That's the 90-line code. It takes forever, and you might make a mistake copying it. But Ang realized you don't need new sheet music. You just tell the computer to take the underlying math of the song and shift every single frequency up exactly one octave.
Yes.
And that perfect mathematical interval, that octave jump, is 0x feet.
That's a perfect analogy. And when you pull back and look at what that implies, it is a profound reminder of the environment we are swimming in every day.
What do you mean?
Well, we look at our screens and we see human language, we see organic, messy communication, but beneath the glass, language has been translated into an absolute rigid geometry.
Right, it's all just math.
Ang didn't invent the relationship between these characters. Ang just noticed the structural harmony of the architecture and decided to use it instead of fighting it.
It is so deeply satisfying to read about. It's like finding a secret tunnel that completely bypasses rush hour traffic. You go from typing out 90 lines of pairs to a single, elegant mathematical truth. You feel like a genius. And this is where the story gets really crazy. Just as you get comfortable with that elegance, Ang completely pulls the rug out.
Yeah, the diary entry pivots hard here.
It goes from this beautiful mathematical optimism into something that feels almost paranoid.
The shift in tone is jarring, for sure, but it is the mark of a seasoned engineer. Because discovering the mathematical truth of your code is only half the battle.
Because your code doesn't live in a vacuum.
Exactly. Your code does not exist in a vacuum. It is going to be saved by a text editor. It is going to be compressed, sent across a network, unzipped by a server, and compiled by a completely different machine in a CI/CD pipeline.
For those who might not know, CI/CD is continuous integration and continuous deployment. It's the automated factory that builds the software.
Right, the factory. And Aang points out a massive trap waiting in that factory. Even after clearing out the 90-line table, there are still a few specific characters that need mapping in the program.
Specifically typographical curly quotes, right?
Yeah, the fancy quotation marks that curve inward around dialogue, like the left quote and the right quote.
Okay, so what's the trap?
Aang explicitly warns the reader, whatever you do not type the literal curly quote symbol into your source code. Do not use the actual character.
Instead, Aang insists on using hexescape codes. So for a left curly quote, instead of typing the actual curvy symbol, Aang writes the string \by2001c.
Right, by 2001c.
And for the full width version, Aang types by 300c, which, to be honest, looks incredibly ugly.
It does. It's not pretty.
We just spent all this time talking about deleting noise and making the code elegant, and now we are typing \x numbers and letters instead of a simple quotation mark. If I'm reviewing that code, I have no idea what x201c is without looking it up.
No one does.
So why intentionally make your code that hostile to human eyes?
To protect it from the machine. Aang is anticipating a very specific, totally devastating type of failure called an encoding mismatch.
Okay, break that down for us.
Well, we assume that when we type a curly quote, the computer just saves a curly quote, but it doesn't. It saves a sequence of bytes based on a specific encoding standard.
Right, the dictionary it uses to translate text to binary.
Exactly. The modern universal standard is UTF-8. And in UTF-8, a curly quote is pretty complex. It actually takes up multiple bytes of data.
How many?
Specifically, it saves as 3 distinct bytes.
Okay, so UTF-8 uses 3 chunks of data to draw that one curvy symbol.
Right. But what happens if the server building your software, that CI/CD pipeline factory, is misconfigured?
So that happens a lot.
All the time. What if it defaults to an older legacy encoding standard like Latin 1?
Okay, and how does Latin 1 handle it?
Latin 1 is primitive. It assumes that every single byte represents one distinct character, period.
Oh no, I see where this is going. If UTF-8 wrote a 3-byte character and Latin 1 reads it,
Latin 1 looks at those 3 bytes meant for a single curly quote, and it interprets them as 3 entirely separate random characters.
oh geez.
Yeah, it might render as like an accented A, followed by a copyright symbol, followed by some unprintable control character.
It's the recipe analogy again.
Exactly.
The ink is the same. The raw binary data on the hard drive hasn't changed at all. But the environment reading the data is using the wrong dictionary.
And the terrifying part is, the compiler doesn't throw an error. It doesn't crash and tell you something is broken. It just silently corrupts your text.
The silent scramble. That has to be the most dangerous bug in software.
It really is. You won't know there is a problem until a user emails you complaining that all the chapter headings in your program look like ancient hieroglyphs.
That's a nightmare.
This is the essence of defensive programming.
Yeah.
You cannot trust the environment. You cannot guarantee that the server compiling your code knows it's supposed to be reading UTF-8.
So how does typing x21c solve the problem?
Yeah.
Why does a broken Latin 1 server read that correctly when it scrambles a normal quote?
Because case 21c is written entirely in basic, primitive ASCII characters.
Oh, I see.
Think about it. It's a backslash, a lowercase x, some numbers, a capital C. Every single encoding standard on the planet, even the most horribly misconfigured legacy Latin 1 environment, agrees on how to read basic ASCII characters.
They all map those specific bytes the exact same way.
Exactly.
So you are basically smuggling the complex character through a hostile environment by disguising it as basic text.
Yes. You are bypassing the text editor's interpretation entirely. By using the hex escape code, Aang is speaking directly to the compiler in an absolute, undeniable language.
It's bulletproof.
Completely. The code forces the compiler to say, look, I don't care what your local encoding settings are. I don't care if you think you are in UTF-8 or Latin 1. I am explicitly commanding you to construct the character located at hexadecimal address 201c.
It takes the power of interpretation away from the fragile environment and locks it safely inside the logic of the code itself.
It is a masterclass in seeing the whole board.
It really is. The first half of this refactoring was all about trusting the math.
Yeah.
Trusting that 0x feet is this universal law within Unicode that you can rely on to delete 90 lines of noise.
Right. Optimism.
But then the second half is about absolutely distrusting the physical reality of the systems around you.
And balancing those two instincts is what separates a good programmer from a great engineer.
You want the logic of your ideas to be as elegant and structurally sound as a mathematical offset, but you have to deliver those ideas in a vehicle armored enough to survive the journey from your local laptop to a production server on the other side of the world.
And the takeaway here, I mean, it goes way beyond Haskell programming. Even if you never touch a line of code in your life, the core lessons of Ang's diary apply to how we all work and communicate.
Absolutely.
We all deal with noisy systems. We all have processes in our jobs that feel like typing out a 90-line mapping table. So the lesson is to step back and look for the 0x feet in your own workflow. Look for the structural rule that makes the brute force labor obsolete. And just as importantly, anticipate the encoding mismatches in your own communication.
Yeah.
You might write the perfect email or, build the perfect presentation, but if the person receiving it is operating in a different context, if they are reading your UTF-8 intent through a Latin 1 lens, the message is going to silently scramble.
It's going to get lost in translation.
You have to build defensive clarity into your work so it survives that translation.
Surviving the translation. That brings up something that has been lingering in the back of my mind since we started talking about 0x feet.
Oh, yeah. What's that?
Well, we just spent all this time marveling at how you can mathematically shift the basic English alphabet into entirely different full-width visual representations just by adding a fixed number.
Right.
The geometry of our digital language is just that rigid. So it leaves me with this final thought for you to mull over. What other hidden, rigid mathematical relationships exist between the incredibly diverse human languages encoded inside our machines?
That is a deep rabbit hole.
Right. If there is an exact, absolute mathematical bridge between a standard X and a full width, are there numerical bridges buried deep in Unicode between concepts in entirely different language families?
It makes you wonder.
And could the growing reliance on these digital coordinates eventually change how we think about the act of translation itself? We're just moving abstract symbols around, or are we slowly mapping out the absolute mathematical coordinates of human thought?
Wow.
It's something to ponder the next time you hit a single key on your keyboard. Thanks for joining us on this deep dive.